Well, for a quick review, let's look at an example problem using the magnetic force. And actually a fairly easy problem viewed one way, but it gives us a good chance to review. So here we want to find the magnitude of the acceleration of an electron that is moving at 1 times 10 to the 7th meters per second in the xy plane at an angle of 30 degrees with the y-axis in a uniform magnetic field of strength 10 Tesla that's also in the plus z direction. So let's take a look at what we're given. Some of it is given, some of it we have to glean. I drew it in the xy plane, and that means z is coming out of the board at me. And we're given that it's an electron, and so I can look up the charge on the electron. It's negative 1.6 times 10 to the minus 19 coulombs. And we might need the mass, so the mass of an electron is 9.11 times 10 to the minus 31 kilograms. And let's see, we're given the velocity, well, or at least the speed, right? We're given the speed is this, but we're given the direction. It makes 30 degrees with the xy plane, or with the y-axis. And so we've got speed v. V is 10 to the 7th meters per second. And this angle that it makes with the y-axis is 30 degrees. So the first thing, after looking up the values and drawing a picture, I've got a velocity vector now, and I know that in the magnetic force, I've got a velocity vector, and so I get the x and y components of this velocity v. The x component, vx, is going to be the opposite over the hypotenuse, and that'll make it v sine 30. The opposite is sine. And Vy, that's this direction, is going to be the cosine, so it'll be the speed cosine 30 degrees. And sine of 30 is a half, cosine 30 is 0.866, and so I get these two for the x and y components of the velocity. And then I'm pretty well set up. I just plug in what my charge is to get the magnetic force. It's minus q. V is Vx in the I hat plus Vy in the J hat. Cross that into the magnetic field, which they give me was 10 Tesla, and that's in the Z direction in the K hat. And I can simply distribute this cross product across this sum, and that gives me minus E Vx B I hat cross K hat. And here I'll get minus E Vy B J hat cross K hat when I distribute this cross product. Cross products distribute across vector sums, but remember cross products are not generally commutative, so A cross B is not equal to B cross A. Okay? So I get this. And now I need to identify what these are. And you can go to that little multiplication table for the cross product, but I think if you work it out, I hat cross K hat, you can use the right-hand rule, and that becomes minus J hat. J hat cross K hat, again, you can use the right-hand rule, that becomes I hat. And when I did that, I get a minus is a plus. V, Y, B, J hat. Minus I, E, V, B, B, I hat. And then I reordered these in the usual way. I usually put the x coordinate first and then the y coordinate over here. So I get this general formula for this particular setup. And I can compute the x and the y components, which I did here because I have all this information. Vy we calculated earlier. E we know, so minus, remember E is the magnitude of the charge, so that's a positive, 1.6 times 10 to the minus 19th coulombs. Vy was 0.5 times 10 to the 7th meters per second. I calculated that earlier. And then B is 10 Tesla. And then I have to know what a Tesla is. One Tesla is 1 Newton Coulomb second per meter. And all the units cancel. This comes down to newtons. And when I multiply this out, I get minus 8 times 10 to the minus 12 newtons. Fy is similar. Get the force, and that's 1.6 times 10 to the minus 19th. By was 0.866, 10 to the 7th, and 10 Tesla. Again, the units cancel, comes down to newtons, and I get 1.39 times 10 to the minus 11. So I get the total magnetic force on this in terms of its x and y components using the unit vector notation as just the sum of these two in the I hat and the j hat. Unfortunately, it didn't ask me for that. What it asked me for was the magnitude of the acceleration. So now I have to remember last semester, force is equal to mass times acceleration. The only force was the magnetic force, which I've got up here. And so the acceleration is just 1 over m times that magnetic force. And the mass was an electron, 9 times the 9.11 times 10 to the minus 11 kilograms. And then the magnetic force was as we calculated above. And then you go through, you can check the units on it, but it does come out in acceleration units, meters per second squared. And when I did the calculation, I get this for the acceleration. So I've really done more than it asked. Now I've got the acceleration vector, but I still haven't done what it wanted, and that's find the magnitude of the acceleration. So let's look at the magnitude of it. Remember, the magnitude of any vector, in this case acceleration, is the square root of the sum of the squares of its components. And so I get the x component squared, the y component squared, square rooted, and when I do that I get the acceleration 1.6 times 10 to the 19th meters per second squared. Now there's another way that I could have done first, and it's actually a little easier. So another way that you might do it is to start with Newton's second law. Take the magnitude of both sides. Mass is always positive, so I get the magnitude of the magnetic force is equal to the mass times the magnitude of the acceleration, which is what it asked for. So the magnitude of the acceleration is F over m, and the force is just the magnetic force, QB cross B. And now then I can do the magnitude of the charge. Charge is actually minus e, so that just becomes the magnitude of that. The speed was 1 times 10 to the 7th. B was 10 Tesla. What's the angle? Well, the velocity vector is in the xy plane, and the magnetic field is pointing in the z direction. So that angle is sine theta is just 90 degrees. The magnetic field is perpendicular to the plane that the v vector is in. And Q is the magnitude of the charge, the mass of the electron, B speed, 1.7 times 10, 1 times 10 to the 7th meters per second. B is 10 Tesla, sine of 90 is 1. And if you do all of that, you get in a much shorter fashion the acceleration. So, and the two agree to within some round off error probably. So the there's always several ways to attack a given problem, and it kind of depends on what they ask as to which way is the shorter. But don't forget these cases where you can take the magnitude of Newton's second law, and then that shortens the process when all that's wanted was the magnitude of the acceleration.